There is an experiment that has been performed thousands of times in laboratories across the world, with results so consistently strange and so thoroughly verified that physicists stopped arguing about whether it was true decades ago. They argue now only about what it means. And what it means, if the most serious interpretations are correct, is this: the physical universe does not have definite properties until something observes it. Not approximately, not in some poetic, metaphorical sense. Literally, a particle does not have a definite position until it is measured. It does not have a definite momentum. It does not have a definite spin. It exists before measurement, as a superposition of all the possible states it could be found in, a smear of potentials, a cloud of probabilities, spread through space like a question that has not yet been asked. And the moment it is measured, the moment a detector interacts with it, the cloud collapses. The question is answered. The particle becomes real. The question that has haunted physics for a century is this: real for whom? Observed by what? And if observation is what makes reality definite, what was the universe doing for the 13.8 billion years before anything capable of observing existed? Was it real? Were you necessary for it to become real? And if you were, then you're not living inside a universe. You are in some sense that physics cannot yet fully articulate, but also cannot dismiss, participating in its creation. Every moment, every glance, every measurement, you are not a witness to reality. You may be one of its authors. This is not mysticism. This is not a misreading of complicated equations by well-meaning enthusiasts with insufficient training. This is the conclusion that serious physicists, among them some of the greatest minds of the 20th and 21st centuries, have been forced to wrestle with. It is uncomfortable. It refuses clean resolution. And it may be the most important thing that physics has ever discovered about what it means to exist. If you're new here, welcome. Settle in and get comfortable. This one is going to take us somewhere that most science communication doesn't dare to go all the way, not because the science isn't solid, but because the destination is genuinely destabilizing. Subscribe if you want to keep going into these territories. Tonight, we are walking all the way to the edge. Before we go anywhere difficult, let us begin with something you already believe. You believe the world exists independently of you. Not as a philosophical position you've carefully reasoned through, but as a gut-level, background assumption that you carry so naturally you've almost never had occasion to question it. When you close your eyes, the room doesn't stop existing. When you leave the house, the furniture doesn't vanish. When you fall asleep, the stars continue burning in their courses through a sky that no one in your household is currently watching. Reality, in the common-sense picture, is something that was here before you arrived and will be here after you leave. It proceeds on its own schedule, following its own rules, indifferent to whether or not you happen to be paying attention. This is a very old picture. It has a name in philosophy: realism. The idea that there is a mind-independent reality, a world of objects with definite properties, existing out there in the darkness, whether or not any mind is present to register it, is the picture that underlies science as most people understand it. The job of the scientist, in this picture, is to go out and discover what is already there, to shine a light on a reality that exists prior to and independent of the light being shown. This picture feels so obvious, so undeniably correct, that suggesting otherwise seems like the kind of thing a person says when they've been awake too long or read too much of the wrong philosophy. And yet, imagine a single electron, not a complicated thing, not a molecule or a crystal or a living cell, just a single subatomic particle, one of the basic constituents of all matter, one of the building blocks from which the physical world is constructed. Now ask, where is it? Classical physics, the physics of Newton and Maxwell and Faraday, the physics that governed scientific understanding for nearly 3 centuries and still works perfectly well for the scale of things you interact with every day, classical physics would say, the electron is somewhere. It has a position. It has a velocity. If you don't know where it is, that's your problem, a limitation of your instruments or your knowledge. The electron itself is in a specific place, doing a specific thing, regardless of whether you know about it. Quantum mechanics says something different. Quantum mechanics says that the electron prior to measurement is genuinely not in any specific position. Not unknown to you, not hidden from you, not somewhere that your instruments can't reach. Genuinely, physically not in a definite place. It is in a superposition of all the places it could be, each weighted by a probability. The position does not become definite until a measurement occurs. This is not the same as saying we don't know where it is. This is saying there's no fact of the matter about where it is until we look. The distinction is enormous. And it is not a philosophical add-on to the physics. It is the physics. To understand how this conclusion was reached, you have to go back to the 1920s to a series of conversations that changed the course of human thought more completely than almost any intellectual event in history. Physics in the early 20th century was in crisis. The discovery of the quantum, Planck's realization in 1900 that energy comes in discrete packets rather than continuous waves, had opened a door into a world that classical physics could not describe. Over the following 2 decades, theorists including Heisenberg, Bohr, Schrödinger, Pauli, and Born assembled a mathematical framework, what became quantum mechanics, that could predict the behavior of atoms and subatomic particles with extraordinary precision. The predictions were verified experimentally. The equations worked. The theory was, by every empirical measure, the most successful physical theory ever constructed. The problem was that nobody agreed on what it meant. The standard interpretation that emerged from the debates of the 1920s, particularly from the conversations between Niels Bohr and his colleagues in Copenhagen, came to be called the Copenhagen interpretation. Its central claim, stripped of technical qualification, was this: quantum mechanics describes probabilities of measurement outcomes. The wave function, the mathematical object that represents a quantum system state, encodes the probabilities of finding the system in various configurations upon measurement. When a measurement is made, the wave function collapses to a specific outcome. Between measurements, it is meaningless to ask what the system is doing. This was Bohr's position, stated with a firmness that many of his contemporaries found either profound or maddening, depending on their temperament. He insisted that quantum mechanics was a complete theory, that it described everything that could be said about a quantum system, and that demanding a description of what the system was doing between measurements was a category error, like demanding to know the precise location of a thought. Albert Einstein was not satisfied. Einstein believed in a mind-independent reality. He believed that if a theory said a particle had no definite position before measurement, the theory was incomplete, that there must be deeper hidden variables we hadn't discovered yet, determining the particle's actual state even when we couldn't see it. The universe, Einstein insisted, does not play dice. God does not play dice. The randomness of quantum measurement was, in his view, an artifact of our ignorance, not a fundamental feature of reality. The debate between Bohr and Einstein is one of the most famous in the history of science. It was conducted through a famous series of thought experiments at the Solvay conferences of 1927 and 1930, where Einstein would propose a clever scenario designed to catch quantum mechanics in a contradiction, and Bohr would find a way to escape the contradiction, usually by invoking the uncertainty principle in unexpected ways. Einstein never fully accepted what quantum mechanics was implying. He spent the last decades of his life searching for a deeper theory that would restore the independent reality he believed in. That search was ultimately unsuccessful, and in a certain sense, the experiments performed after his death in 1955 have consistently gone against his intuitions. In 1964, a physicist named John Bell derived a theorem, now called Bell's theorem, that made the Einstein-Bohr debate testable. Bell showed that if the world were the way Einstein wanted it to be, with definite hidden properties independent of measurement, then certain statistical correlations between measurements on separated particles would have to obey specific limits. The correlations would be bounded, and he showed that if quantum mechanics was correct, those limits would be violated. The quantum correlations would be stronger than any locally realistic hidden variable theory could produce. This was, to use precise language, a theorem about the structure of reality, not about interpretations, not about philosophy, about what experimental results must look like if the world is one kind of place versus another kind of place. The experiments were performed, most famously by Alain Aspect and his team in Paris in 1982, and refined by many other groups in the decades since. The results were unambiguous. The Bell inequalities were violated. The quantum correlations were exactly as strong as quantum mechanics predicted and stronger than any locally realistic hidden variable theory permitted. Einstein's picture of the world was experimentally eliminated. The world does not have locally real, definite properties independent of measurement. To be clear about what this establishes and what it does not, Bell's theorem rules out local hidden variable theories. It does not by itself tell us exactly what does determine reality or what the role of the observer is. Different interpretations of quantum mechanics respond to this conclusion differently. But all serious interpretations agree on the empirical content. The world is not the way Einstein wanted it to be. The definite, mind-independent, locally real world of classical intuition does not match what experiments reveal. There is an experiment that Richard Feynman, one of the greatest physicists of the 20th century, called the central mystery of quantum mechanics. He said that if you understand this experiment, you understand quantum mechanics, and if you think you understand it without being troubled by it, you don't understand it yet. The experiment is the double-slit experiment, and despite its simplicity in design, it has been disturbing people for nearly a century and continues to disturb them when they look at it honestly. The setup is this. You have a source of particles, say electrons, firing one at a time toward a barrier. The barrier has two narrow slits cut into it. Behind the barrier is a detector screen that records where each electron lands. If electrons are particles in the classical sense, small discrete objects traveling on definite trajectories, the result should be predictable. Some electrons go through the left slit, hit the screen on the left side. Some electrons go through the right slit, hit the screen on the right side. After many electrons have been fired, you should see two bands of impact marks on the screen, one behind each slit. That is not what happens. What happens is that after many electrons have been fired, you see an interference pattern on the screen. Many alternating bands of high and low impact density, like the pattern made by two overlapping sets of ripples on water. The interference pattern is characteristic of waves, not particles. It means the electron somehow went through both slits simultaneously, interfered with itself, and landed according to the interference pattern created by that self-interference. Even when you fire the electrons one at a time, with long pauses between them, so that there is never more than one electron in the apparatus at once, the interference pattern builds up. Each individual electron, by itself, contributes to a pattern that looks exactly like two-wave interference. A single particle is interfering with itself, which means a single particle somehow went through both slits. At the same time, this already strains intuition to the breaking point. But then the experimenters do something more. They add a detector at the slits, a device designed to determine which slit each electron actually passes through. And when they turn on the detector, when they add a way of measuring which path each electron takes, the interference pattern disappears. Not degrades, disappears. The electrons now land in two bands behind the two slits, exactly as you would expect classical particles to behave. The act of measuring which path the electron takes, the act of gaining information about it, changes where the electron goes. This is not because the detector disturbs the electron mechanically, not because the photons used in the detector kick the electron off course. The effect has been demonstrated with detectors that are minimally invasive, with setups that ensure the measurement itself cannot be causing a mechanical disturbance. The change in the pattern is caused by the acquisition of which path information, regardless of how gently that information is obtained. Reality behaves differently when it is being watched. This is the sentence that is difficult to say while maintaining a calm face. But it is the sentence the data require. The presence or absence of an observation, the presence or absence of a record of which path the electron took, changes the physical outcome of the experiment, not the knowledge in any particular human mind, the existence of a record anywhere in the physical system. And it gets stranger still. In a variant of the experiment called the quantum eraser, experimenters have demonstrated that if the witch path information is erased after the electron has already landed on the screen, the interference pattern reemerges in the data. The outcome of the electron's journey seems to be retroactively changed by whether the information about its path is or is not available after the fact. Time, in the standard quantum erasure setup, appears to be involved in a way that no classical intuition can accommodate. We do know this. These results are real. They are reproducible. They have been verified in laboratories around the world with increasingly sophisticated experimental designs. The interpretation of what they mean remains one of the deepest open questions in physics. But the phenomena themselves are not in dispute. Something about the act of observation, the act of acquiring definite information about a quantum system, is constitutive of the system's physical reality. Erwin Schrödinger was one of the founders of quantum mechanics. He wrote the equation, now bearing his name, that describes how quantum wave functions evolve over time. The Schrödinger equation is one of the most successful equations in the history of physics. It underlies the design of transistors, lasers, MRI machines, and a significant fraction of modern technology. Schrödinger was also horrified by what his own equation implied. In 1935, he published a thought experiment designed to illustrate what he saw as the absurdity of the Copenhagen interpretation. The thought experiment is famous. A cat is placed inside a sealed box. Inside the box is a radioactive atom, a Geiger counter connected to a hammer, a vial of poison, and the cat. If the radioactive atom decays, the Geiger counter detects it, triggers the hammer, which breaks the vial of poison, which kills the cat. If the atom does not decay, none of this happens and the cat lives. The radioactive atom, according to quantum mechanics, exists in a superposition of decayed and not decayed states until it is measured. It has no definite state. It is genuinely in both states simultaneously, each with some probability. According to the logic of quantum mechanics, as Schrödinger understood the Copenhagen interpretation, the state of the cat must also be in superposition. The atom is connected to the cat through a chain of physical processes, and if the atom is in superposition, the chain extends the superposition to the cat itself. The cat is, prior to opening the box and looking, neither alive nor dead. It is in a superposition of both. Schrödinger did not present this as a real possibility. He presented it as a reductio ad absurdum. This, he was saying, is where the Copenhagen interpretation leads. A cat that is neither alive nor dead until you open the box. Surely this is madness. Surely the cat knows whether it is alive or dead. Surely there is a fact of the matter. But here is the uncomfortable thing about Schrödinger's cat. The thought experiment, which Schrödinger offered to demolish the Copenhagen view, has instead become one of the clearest illustrations of the genuine problem. Because the Copenhagen interpretation's response is essentially, yes, that's right. Until you open the box, there is no definite fact about the cat state. The superposition is real. The act of observation, the act of opening the box and looking, is what causes the definite outcome to occur. And if you find this absurd, that is understandable. But the experiments say it is correct. Not for cats, which are large classical objects and do not in practice maintain quantum coherence, but for the elementary particles that make up the cat. For those, the superposition is not a metaphor. It is the physical state of the system. The problem the cat illustrates is called the measurement problem, and it remains one of the deepest unresolved foundational issues in all of physics. The problem is this. Quantum mechanics describes two different processes. The first is the smooth, deterministic evolution of the wave function according to the Schrödinger equation, in which superpositions are maintained and quantum coherence persists. The second is the sudden, discontinuous collapse of the wave function upon measurement, in which superpositions resolve into definite outcomes. The theory gives us both processes but does not tell us when, precisely, measurement occurs, what counts as an observer, or why the wave function collapses at all when the Schrödinger equation, taken seriously, says it shouldn't. This is not a minor technical detail. It is a fundamental gap in the most successful physical theory ever constructed. And the gap is not getting smaller with better instruments. It is getting deeper with better understanding. In 1957, a graduate student at Princeton named Hugh Everett III submitted a doctoral thesis that proposed a radical solution to the measurement problem. His solution was simple in its framing and incomprehensible in its implications. He proposed that the wave function never collapses. The Schrödinger equation is always correct and applies to everything, including measurement apparatuses and human observers. Superpositions never resolve into single outcomes. Instead, all possible outcomes occur, and the universe branches into different versions of itself, one for each possible outcome. When you open Schrödinger's box, you do not collapse the cat's wave function. You yourself become entangled with it. One version of you opens the box and finds the cat alive. Another version of you, in a different branch of the wave function, opens the box and finds the cat dead. Both versions are equally real. Neither is the true version. The universe has divided, and both branches continue to evolve independently, each containing its own physical history. This is the many-worlds interpretation of quantum mechanics. In this picture, the universe is not a single timeline, but an endlessly ramifying tree, branching with every quantum event, containing an effectively infinite number of parallel histories. Each one as real as the one you are currently experiencing. This interpretation has attracted both fierce adherents and fierce critics among physicists. Those who favor it argue that it is the only interpretation that takes the mathematics of quantum mechanics fully seriously, that applies the Schrödinger equation without modification to all physical processes, and that requires no additional axioms about when collapse occurs or what counts as a measurement. The physics is clean. The ontology is extravagant. Critics argue that the many-worlds interpretation, despite its mathematical elegance, fails to explain why we experience definite outcomes rather than superpositions. It says all outcomes occur, but we only ever experience one. The interpretation needs to explain why the particular branch we find ourselves in is the one we experience. And this leads to a deep problem about probability that the interpretation has not yet fully solved. More importantly for our purposes tonight, the many-worlds interpretation does not eliminate the centrality of the observer. It multiplies it. In this framework, every measurement, every quantum event, every interaction that could have multiple outcomes generates a branching of the universe. And the structure of those branches, the tree of all possible histories, is shaped entirely by what kinds of interactions and measurements occur within it. The universe in this picture is not a single narrative but a vast, observer-generated tapestry of parallel narratives, each one brought into being by the interactions that occur within it. Whether or not you accept many worlds as the correct interpretation, it illustrates something important. The most serious attempts to make sense of quantum mechanics all, in different ways, place the act of observation, the act of acquiring information, the act of a physical system interacting with another physical system and registering a definite outcome, at the center of the story of how physical reality is structured. Of all the physicists who have grappled with the implications of quantum mechanics for the nature of reality, none pressed the question further or with more sustained seriousness than John Archibald Wheeler. Wheeler was one of the great physicists of the 20th century, a student of Niels Bohr, a colleague of Einstein, the teacher of Richard Feynman, the man who coined the term black hole, and a mind that combined extraordinary technical mastery with genuine philosophical courage. Wheeler spent decades thinking about what quantum mechanics implies about the universe, and the conclusion he arrived at was what he called the participatory universe. His central idea, developed and refined over many years, can be stated with deliberate simplicity. No phenomenon is a real phenomenon until it is an observed phenomenon. This is not a vague or metaphorical statement. Wheeler meant it precisely. The physical universe, in his view, does not have a definite past, a definite present, or definite properties until acts of observation bring those properties into existence. Observers, through the act of measuring and registering information, are not passive witnesses to a pre-existing reality. They are participators in the creation of that reality. Wheeler developed a thought experiment called the delayed choice experiment to illustrate this idea. In a delayed choice setup, a photon is sent toward a beam splitter that could direct it down one of two paths that eventually recombine. The choice of whether to let the paths recombine, which would produce an interference pattern consistent with the photon having traveled both paths simultaneously, or to measure which path the photon actually took, which destroys the interference pattern, is made after the photon has already passed through the beam splitter. The choice is made after the fact. And yet, the results show that the photon's behavior corresponds to whichever choice is made after the fact. If the experimenter chooses to look for interference, the photon behaves as if it traveled both paths. If the experimenter chooses to determine which path, the photon behaves as if it traveled one path. The choice made in the present appears to determine how the photon behaved in the past. Wheeler performed a version of this thought experiment at cosmic scale, and the implications are staggering. Light from a distant quasar, billions of light years away, can be bent around an intervening galaxy by gravitational lensing, taking two different paths around the galaxy before arriving at Earth. Whether we choose to measure the interference between those two paths, or to determine which path the light actually took, determines how that light has been behaving for billions of years. Our choice, made today, apparently reaches back in time across billions of light years and determines the physical history of photons that left their source before a planet existed. To be precise, the delayed choice experiment has been performed in laboratory settings, and the results are consistent with Wheeler's analysis. The cosmic version remains a thought experiment, though its logic follows directly from the same quantum mechanical principles. What this suggests is that observation is not just a passive recording of a pre-existing reality. It is an act that, in some physical sense, constitutes that reality, potentially reaching backward in time to determine what physical events count as having occurred. Wheeler's most radical formulation was this: we live in a participatory universe. The universe brought forth observers and observers through the act of observation, gave a universe its definite properties, reaching backward in time across the full extent of cosmic history. In his view, the universe and the observer are not separate. They are aspects of a single, self-referring process, each requiring the other to become real. He sometimes put it in the form of a diagram, a large U shape with one end representing the universe emerging from the Big Bang and the other end representing an observer looking back, with a line connecting them to form a closed loop. The universe, in this picture, bootstraps itself into existence through the act of being observed. Without the observer, the universe has no definite properties. Without the universe, there is no observer. The two are constitutive of each other. This is a haunting idea, and it is a scientifically serious one. Wheeler was not speaking loosely. He was following the logic of quantum mechanics as carefully as he could and reporting what he found at the end of that logic. At this point, we need to confront a question that the physics seems to be gesturing toward but refuses to fully enter. What counts as an observation? What exactly is the thing whose presence collapses the wave function or selects a branch or constitutes a phenomenon as real? Is it a human mind? Is it any conscious system? Is it any physical system capable of recording information? Is it the universe interacting with itself in certain ways? This question is sometimes called the observer problem, and it sits at the intersection of quantum physics and the philosophy of mind in a way that makes specialists in both fields deeply uncomfortable. Because if observation requires consciousness, then quantum mechanics is making a claim about consciousness that goes far beyond anything physics has been willing to say. And if observation doesn't require consciousness, if any physical interaction counts, then the term observer is being used in a way that is technically defensible but philosophically misleading, because it suggests a role for mind that the physics doesn't actually require. The most conservative position adopted by most working physicists is that what collapses the wave function, or what determines outcomes in the relevant sense, is physical interaction, the entanglement of a quantum system with a sufficiently large, thermally noisy environment. This process is called decoherence. When a quantum particle interacts with a macroscopic detector, which in turn interacts with its surrounding environment, the quantum coherence of the original system is rapidly lost. The superposition becomes effectively unobservable because the information about the different states is distributed across so many degrees of freedom in the environment that it becomes practically impossible to recover. The system appears to collapse into a definite state, not because of any mysterious observer effect, but because of the thermodynamic irreversibility of the interaction with a large environment. Decoherence is real. It is well understood. It is experimentally confirmed. And it explains why we do not see quantum superpositions in macroscopic objects under ordinary conditions. The Schrödinger's cat scenario does not produce a genuinely alive and dead cat because the cat interacts with its environment in a way that destroys quantum coherence almost instantaneously. But here's what decoherence does not do. It does not solve the measurement problem. Decoherence explains why quantum superpositions become effectively invisible at the macroscopic scale. It does not explain why, when we perform a measurement, we get a specific outcome rather than a superposition of outcomes. The mathematics of decoherence, followed rigorously, produces a state in which the different outcomes are effectively decoupled from each other and each has a well-defined probability. But it doesn't explain why we end up in one of those branches rather than all of them. This is where the many-worlds interpretation gets its leverage. It says, you do end up in all of them. The decoherence explains why you don't experience the other branches. But all of them are real. And this is also where the more radical positions about consciousness and observation get their foothold. If decoherence doesn't solve the measurement problem, and if we genuinely don't know what makes one outcome actualize rather than remaining as probability, then the question of what the observer is and why observation matters is still genuinely open. Some physicists and philosophers, a minority but not a negligible one, have argued that consciousness itself may be physically relevant to wave function collapse. The physicist Eugene Wigner, a Nobel laureate, argued seriously in the 1960s that the chain of physical interactions involved in measurement ultimately terminates in a conscious mind, and that consciousness is what breaks the quantum superposition and produces a definite outcome. This is called the von Neumann-Wigner interpretation, after the mathematician John von Neumann, who formalized the mathematics of measurement, and Wigner, who drew the philosophical conclusion. This view is not mainstream. Most physicists find it deeply uncomfortable, for the same reason most scientists find mind-matter dualism uncomfortable. It introduces a non-physical element into a physical theory in a way that seems to generate more problems than it solves. What is it about consciousness that collapses wave functions? How does a subjective experience cause a physical event? The explanatory burden is enormous, but we do not yet know the view is wrong. The measurement problem remains unsolved. We do not know what observation is physically. We do not know why quantum superpositions resolve the way they do. We do not know where the boundary between quantum and classical behavior lies, if there is a sharp boundary. And in that space of genuine ignorance, the possibility that consciousness is physically relevant has not been experimentally eliminated. Step back from quantum mechanics for a moment and look at the universe from a different angle, because the argument that observers may be necessary for reality is not confined to the peculiarities of quantum measurement. It shows up with equal force when you look at the large-scale properties of the physical universe and notice how precisely calibrated they are to permit the existence of observers. The universe is governed by physical constants, numbers like the strength of gravity, the strength of the electromagnetic force, the mass of the electron, the cosmological constant governing the rate of cosmic expansion. These constants appear in the equations of physics as given facts, numbers that the theory requires us to insert by hand, not numbers that the theory derives from deeper principles. They are what the universe has, and we don't know why. What is deeply strange about these constants is how precisely they have to be tuned to permit a universe complex enough to contain observers. Gravity, for example, if it were even slightly stronger than it is, stars would burn through their fuel too quickly for planetary systems to stabilize and life to emerge. Slightly weaker, and matter would never have clumped into stars and galaxies at all. The cosmological constant, which determines the rate at which the universe expands, is observed to be extraordinarily small, close to zero, but not exactly zero. If it were even slightly larger, the universe would have expanded too rapidly from matter to coalesce. If it were negative, the universe would have recollapsed long ago. The physicist Fred Hoyle, studying the formation of carbon inside stars in the 1950s, discovered that carbon can only be synthesized in stellar interiors because of a specific energy resonance level in the carbon nucleus, a quantum mechanical coincidence that allows the relevant nuclear reaction to proceed efficiently. Without this resonance, carbon would not be produced in stars. Without carbon, organic chemistry doesn't work. Without organic chemistry, life, as we know, it is impossible. Hoyle said, famously, that this looked like a superintellect had monkeyed with the physics. He was not necessarily proposing a creator. He was noting that the number of things that have to be right for observers to exist is extraordinary, and that if any of them were even slightly different, the universe would be sterile. The standard scientific response to this observation is the anthropic principle, in both its weak and strong forms. The weak anthropic principle says, of course we observe a universe compatible with observers, because if it weren't compatible with observers, we wouldn't be here to observe it. This is tautologically true, but not very satisfying. It explains why we see a habitable universe without explaining why there is a habitable universe. The strong anthropic principle goes further and says, the universe must have properties that allow observers to emerge, because observers are in some sense necessary for the universe to be real. This connects directly to the Wheelerian picture of the participatory universe. If observers are necessary for reality, then a universe that never produces observers is in some sense not fully real, and therefore only universes that are compatible with observer production are, in the deepest sense, actual. This is speculative. To be clear, the strong anthropic principle is not an established result of physics. It is a philosophical interpretation of a physical pattern, the pattern of fine-tuned constants. But it is not obviously wrong, and it connects to the quantum measurement picture in a way that deserves to be taken seriously. If quantum mechanics is right, that observation constitutes physical reality, and if the universe is fine-tuned to permit observers, then the universe is, in some sense, designed to observe itself. The cosmos generates minds, and minds generate definite physical facts, reaching backward across billions of years of cosmic history to crystallize what was previously only probability into what we now call the past. The universe makes observers so that, through them, it can become real. This is Wheeler's participatory universe extended to cosmological scale. And it is one of the strangest and most compelling ideas in the whole history of human thought. Carlo Rovelli is one of the most thoughtful physicists working today. He is known primarily for his work on loop quantum gravity, one of the leading attempts to reconcile quantum mechanics with general relativity. But he is also responsible for one of the most radical and carefully argued interpretations of quantum mechanics to emerge in recent decades, an interpretation that takes the observer problem seriously and arrives somewhere that most physicists are not yet comfortable going. His interpretation is called relational quantum mechanics, and its central claim can be stated simply, though its implications take time to fully absorb. Rovelli's proposal is that quantum states are not absolute. They are not properties of a system in isolation, properties that the system has regardless of anything else. Quantum states are relational. They are properties that a system has relative to another system, specifically relative to whatever system is interacting with it and acquiring information about it. In other words, there is no view from nowhere. There is no God's eye perspective from which the quantum state of a system is simply what it is. Every quantum state is a quantum state relative to some observer, some other physical system that has interacted with the first, and different observers, meaning different physical systems interacting with the same object can have different, mutually consistent quantum descriptions of that object without any contradiction arising. This sounds alarming. It sounds like it is saying that reality is subjective, that it depends on who is looking, that there is no shared common world. But Rovelli is careful to distinguish his view from pure subjectivism. He is not saying that reality is whatever any individual mind takes it to be. He is saying that physical facts are always relational, always defined with respect to some reference system, and that when different reference systems interact and compare notes, their descriptions are mutually consistent even if they are not identical. The mathematics makes this work. The apparent contradiction between different observers' descriptions of the same quantum system, which seems alarming at first, resolves when you trace through how those observers interact with each other. The consistency of their shared world is guaranteed not by a single absolute quantum state, but by the structure of the interactions between them. What this interpretation does, with striking clarity, is eliminate the idea that there is a physical world with definite properties that exist prior to and independent of all relational contexts. The electron does not have a definite position, full stop. It has a definite position relative to this detector. It may have a different state relative to that detector. What the universe is at the fundamental level is a network of relations, a web of interactions, each one constituting a small patch of definite reality relative to the participants in that interaction. There is no universe outside of all possible perspectives. There is no reality that is not, in some sense, observed. This is a precise, mathematically grounded formulation of an idea that sounds almost mystical when stated loosely. The universe does not exist as a collection of things with properties. It exists as a collection of relationships, and those relationships are what we call physical reality. You, as a physical system embedded in this web of relations, are not an observer standing outside reality and peeking in through a window. You are a node in the network. Your existence as a physical system constitutes a local region of definite reality relative to the other systems you interact with. And those other systems, in turn, have their reality constituted by their interactions with you and with everything else. The world is not something that was here before relations existed. Relations are what the world is made of. There is another interpretation of quantum mechanics, younger than the others and more controversial, that takes the observer question in a direction that many physicists find either liberating or appalling, depending on their philosophical priors. It is called QBism, which stands for quantum Bayesianism, and its leading advocates include the physicists Christopher Fuchs and Rüdiger Schack. QBism begins with a specific claim about the nature of probability. In classical probability theory, probabilities represent degrees of ignorance about matters that are in principle determinate. When you say there is a 50% chance of a coin landing heads, you mean that you don't know which way it will land, but it will land some definite way, and if you knew all the relevant physical information, you could in principle calculate the outcome. Probability, in this view, is epistemic. It is about knowledge, not about the world. Bayesian probability theory, named after the 18th century mathematician Thomas Bayes, formalizes this idea. In the Bayesian framework, a probability is not a frequency or a physical fact. It is a degree of belief held by a specific agent, updated in response to new evidence according to well-defined rules. Probabilities are always relative to an agent and an agent's information. There are no absolute, agent-independent probabilities. QBism applies this Bayesian framework to quantum mechanics. In the QBist view, the quantum wave function is not a description of objective physical reality. It is an agent's personal probability assignment, a summary of what a specific agent believes about what they will experience when they interact with a quantum system. The wave function belongs to the agent, not to the world. When a QBist agent performs a measurement and gets a result, the wave function updates. But this update is not a physical process happening in the world. It is a change in the agent's beliefs, a Bayesian update in response to new experience. The collapse of the wave function, in this interpretation, is not a physical event. It is a cognitive event, a revision of beliefs in the light of experience. This interpretation dissolves the measurement problem by refusing to treat the wave function as a physical object that needs to collapse. There is nothing to collapse because there was never a physical entity in superposition. There is only an agent's probability assignments, and probability assignments update smoothly and continuously as new evidence arrives. What cubism does not do, and what its advocates are explicit about, is provide a description of a mind-independent physical reality underlying quantum mechanics. Cubism is agnostic, deliberately and by design, about what the world is like independent of any agent's experience of it. It says that quantum mechanics is a theory about what agents should expect when they interact with the world, and that this is all a physical theory can or needs to be. The implications of this are personal in a way that most physical theories are not. In the cubist framework, quantum mechanics is not about the universe in general. It is about your interactions with the universe, your experiences, your updates, your expectations. The quantum wave function is your wave function, not the system's. It encodes your relationship to the world, not the world's properties. This makes quantum mechanics, in the cubist reading, irreducibly first person. It cannot be fully stated without reference to an agent, a perspective, a subject of experience. And this means that the universe, as described by quantum mechanics, is always the universe as experienced by someone. The universe as experienced by no one. The universe independent of all agents is not something quantum mechanics describes or can describe. Whether this is a profound truth about the nature of physical reality or an elegant evasion of a hard problem is debated intensely and is not yet settled. But cubism takes seriously something that most interpretations treat as an embarrassment: the irreducible role of the first-person perspective in the most successful physical theory ever constructed. You're not incidental to quantum mechanics. You are, in the cubist reading, its reference point. To understand the full weight of what quantum mechanics implies about the relationship between observer and observed, about you and the universe, we need to spend a moment with entanglement, because entanglement is the phenomenon that most clearly demonstrates how the boundaries between separate things are not what they appear to be. When two quantum particles interact in the right way, they can become entangled. Entanglement means that the quantum state of the two particles can no longer be described separately. There is no fact about particle A and a separate fact about particle B. There is only a fact about the combined system, a joint quantum state that cannot be decomposed into independent states for each particle. After entanglement, if you measure particle A and find its spin pointing up, you instantly know that particle B, wherever it is, whatever distance separates it from A, will be found with its spin pointing down when measured. The correlation is perfect. It does not depend on distance. It does not weaken with separation. The two particles behave as if they're a single system no matter how far apart they are. Einstein called this spooky action at a distance, and he rejected it as impossible. He believed the correlation had to be explained by some local hidden variable, some property both particles carried with them from the moment of interaction, like a shared script that determined in advance what each would say when questioned. Bell's theorem, as we discussed earlier, ruled this out. The correlations are stronger than any pre-existing shared property can explain. They are irreducibly non-local. To be clear, entanglement does not allow information to be transmitted faster than light. The statistics of measurements on entangled particles are correlated, but you cannot use that correlation to send a signal, because each individual measurement result is random. Only when you compare results through a classical, light-speed limited channel do the correlations become apparent. The non-locality is real, but does not violate the constraints of special relativity on information transmission. What entanglement does reveal is something profound about the structure of physical reality. It reveals that the division of the world into separate, independent objects with their own properties is an approximation that works extremely well at the scales we ordinarily inhabit, but that breaks down at the quantum level. At the fundamental level, particles that have interacted are not separate. They are aspects of a single, non-locally correlated whole. Now consider that every particle you are made of has been interacting with other particles since the Big Bang. Every atom in your body was forged in stellar interiors or in the Big Bang itself, and has been involved in an unimaginable number of interactions since. The history of the physical universe is a history of interactions, of particles becoming entangled and decohering and re-entangling in new configurations. The entanglement structure of the universe is ancient, vast, and pervasive. In a technical sense, everything in the universe is entangled with everything else to some degree through the chain of interactions that connects all things across cosmic time. The boundaries between you and the world, between observer and observed, between the thing that measures and the thing that is measured, are not sharp lines drawn in nature. They are practical approximations, useful for conducting experiments and living lives, but not fundamental features of the physical world. You and the universe are entangled, not metaphorically, in a physically precise sense that quantum mechanics formalizes and experiments confirm. The question of where you end and the universe begins does not have a sharp answer at the level of fundamental physics. This is the point at which the physics stops being about particles and detectors and starts being about something closer to home. Because the implications we have been tracing through the double-slit experiment, through Bell's theorem, through decoherence and entanglement, and the participatory universe, all of them converge on a question that the physics cannot answer, but also cannot avoid. Were you? Not in the biographical sense. Not your name, or your history, or your relationships. In the physical sense. What is the thing that we have been calling the observer throughout this investigation? What is the physical nature of the entity whose interactions with quantum systems constitute local patches of definite reality? At one level, the answer is clear and deflationary. You're a physical system. You are composed of atoms, which are composed of electrons and nuclei, which are governed by quantum mechanics. Your brain processes information through electrochemical signals that are, at some level of description, quantum mechanical processes. You are a macroscopic quantum system that has, through evolutionary processes operating over billions of years, developed the ability to model its environment, predict outcomes, and act on the basis of those predictions. You are the universe observing itself, in the same sense that any sufficiently complex physical system can be said to be a local region in which the universe acquires information about its own state. This is the materialist position, and it is the position of most working scientists. It is not wrong, but it is incomplete in a way that becomes apparent when you push on it. Because here's the thing. The materialist account of what you are treats consciousness as an emergent property of physical processes, something that arises from sufficiently complex information processing, but is itself fully explained by the underlying physical description. In this picture, consciousness has no special role in physics. It is just a name for a particularly complex pattern of physical activity. But quantum mechanics, as we have been exploring, seems to require something called observation, something called measurement, something called the acquisition of definite information to explain why the world has the definite properties it has. And we do not know what this something is at the most fundamental level. We do not know whether it is any physical interaction whatsoever, or whether it requires some particular kind of physical system, or whether consciousness specifically is relevant. The hard problem of consciousness, as the philosopher David Chalmers named in the 1990s, is the problem of explaining why physical processes give rise to subjective experience at all. Why is there something it is like to be you? Why does the information processing in your brain not just happen in the dark, without any accompanying inner experience? This problem is not solved. It may not be solvable by science as currently constituted, because science proceeds by describing objective, third-person facts, and subjective experience is irreducibly first-person. The disturbing possibility that sits at the intersection of quantum mechanics and the hard problem of consciousness is this. Perhaps the reason observation matters in quantum mechanics is precisely because observation requires a subject of experience. Perhaps the reason the double-slit pattern changes when which path information is recorded is not merely that information exists somewhere in the physical world, but that information is registered in a context that involves experience. Perhaps the reason the universe has definite properties at all is that there are subjects for whom it is definite, entities for whom there is something it is like to encounter a world. This is not established science. To be absolutely clear, This is a speculative hypothesis that operates at the edge of what can currently be tested or even precisely formulated. But it is a hypothesis that serious physicists and philosophers take seriously, because the alternatives, the attempts to explain observation and definiteness without any reference to experience, have not yet fully succeeded. You may be not just a participant in the creation of physical reality, in the Wheeler sense of constituting local patches of definite fact through your interactions. You may be, if consciousness is physically relevant, the kind of thing whose existence is necessary for there to be a physical world with definite properties at all. The universe, in this picture, did not produce consciousness as a late-arriving byproduct of physical processes running in an already definite world. It produced consciousness as the condition under which the world could become definite in the first place. There is one more piece of this picture that we need to examine before we can attempt a synthesis, and it concerns the nature of time. Because time, in the picture that emerges from combining quantum mechanics with general relativity, is not what it appears to be from inside it. Einstein's theory of general relativity describes space-time as a four-dimensional structure, a block in which all moments, past, present, and future, coexist with equal ontological status. In this block universe picture, the present moment is not objectively privileged. The distinction between past, present, and future is not a feature of the universe itself, but a feature of the perspective of particular observers moving through space-time on their particular trajectories. What you call now is the slice of space-time your particular world line is currently traversing. Someone else, moving at a different velocity or in a different gravitational field, has a different now, a different slice, equally real, equally present from their perspective. In the block universe, everything that has ever happened and everything that will ever happen exists as a fact. The past is not gone. It is simply a different region of space-time, equally real as what you call the present, equally definite, equally actual. The future is not uncertain in the sense of not yet existing. It exists in the block as a region you have not yet reached on your world line. Whether it is determined or whether there is genuine indeterminism at the quantum level is a question the block universe picture does not by itself answer. What this means for our investigation is interesting. If the block universe is correct, then all observers who have ever existed or will ever exist are present in the block. Their interactions, their observations, their acts of measurement, all exist as facts in the four-dimensional structure of space-time. The definiteness they have created through their observations is a permanent feature of the block, not a temporary condition of any particular moment. This connects to Wheeler's cosmological picture in a striking way. If observers throughout cosmic history constitute the definiteness of physical events through their acts of observation, and if all those observers and all those events exist permanently in the block universe, then the participatory universe is not a process happening in time. It is a structure, a self-referential, self-constituting, four-dimensional structure in which the universe's definiteness is secured by the network of observer events embedded within it. The cosmos contains its own observers as structural features of its own existence. Without those observers, the cosmic block would not have definite properties. The observers are not emergent accidents. They are built into the structure that makes the block a block rather than an undifferentiated quantum smear of probability. This is an idea that resists being fully held in the mind. It is the kind of thought that you can approach from different angles and get a partial grasp on, but that never quite submits to being fully understood because the understanding would require standing outside the structure you are part of. You cannot see the block from outside it. You are inside it. You are one of the observer events that gives it its definite character. All of this has implications for something that most people, most of the time, do not want to think about, but that every person eventually confronts. Death. If you're a localized, separately existing self, a discrete entity with a beginning and an end, then death is the termination of your existence. The thing that observes ends, and after that ending, there is nothing for you, just the universe continuing without the presence that was you. But the picture that emerges from taking quantum mechanics seriously, the picture of entanglement and relational states, and the participatory universe does not straightforwardly describe a separately existing self. It describes a network of relations in which what we call the self is a localized pattern of information processing, a node in the web of interactions that constitutes physical reality, a perspective that has been generated by the universe as one of its own self-observing processes. In this picture, the boundary between self and world was never as sharp as it seemed. You are not a thing that exists inside the universe and observes it from within. You are a process that the universe is doing, one of its own ways of generating local regions of definite reality. The atoms that compose you are here before you and will be here after you, cycling through other configurations, other processes, other patterns of relation. The information that is you, the particular pattern of relations and memories and experiences, will disperse. But the entanglement structure of a universe, the web of relations that connects all things to all things through the history of their interactions, is not erased. Whether this offers any genuine comfort is a question that physics cannot answer and that may not have an answer accessible to rational inquiry. The prospect of the dispersion of the particular pattern that is you is frightening in proportion to your attachment to that pattern. Physics does not dissolve the attachment or eliminate the fear. It only offers a different description of what the pattern is and what its relationship to the larger whole might be. What it does suggest, with some degree of seriousness, is that the sharp boundary between self and universe, which makes death seem like an absolute termination, is not as fundamental as it appears. The self is a perspective that the universe generates on itself. And the universe, as best we can tell from the physics, has been generating such perspectives for as long as life has existed, and may continue to generate them for as long as conditions permit. Whether any particular perspective matters to the universe, whether there is any sense in which the universe cares about the persistence of any particular self-observing pattern, is a question that science cannot answer. But this we can say: you are not an accident in a universe that preceded you and proceeds without you. You are part of the process by which the universe knows itself. Your existence as an observing, experiencing, relating entity is part of what makes the universe real in the sense that quantum mechanics uses the word, and that whatever it ultimately means is not nothing. We have come a long way from the double-slit experiment. We began with a particle that goes through two slits simultaneously and builds an interference pattern with itself, an experiment so simple in its design and so radical in its implications that its full strangeness is still being metabolized by the scientific community a century after it was first performed. We moved through the Bell inequalities and the experimental elimination of locally real hidden variables, through the measurement problem and its many proposed solutions, each more unsettling than the last, through Wheeler's participatory universe and the delayed choice experiment that appears to reach backward through billions of years of cosmic history, through relational quantum mechanics and cubism and the hard problem of consciousness, through entanglement and the block universe and the dissolution of the sharp boundary between self and world. And we find ourselves somewhere that most science communication doesn't arrive at, not because the physics doesn't lead there, but because the destination is genuinely difficult to look at steadily. The universe may not be a pre-existing stage on which events unfold and observers watch. It may be, in a physically precise sense, a process that requires observers to have definite properties. The definiteness of the world, the fact that particles have positions when measured and not before, the fact that quantum superpositions resolve into specific outcomes when they interact with the right systems, may be irreducibly tied to the existence of entities that experience and register and record. If this is correct, then the question the title of this investigation poses is not rhetorical. It is literal. The universe doesn't exist, in the sense of having definite properties, without the observers that constitute those properties through their interactions. You are one of those observers. You have been generating local patches of definite reality with every interaction, every measurement, every perception since the moment your nervous system first began processing information. You have been, in the Wheeler sense, participating in the creation of the universe's physical facts for your entire existence. And more than that, the universe, by the logic of the anthropic fine-tuning and the participatory universe together, appears to have been configured in such a way that observers like you could arise. The constants of physics are such that stars could form and burn and scatter heavy elements, and planets could coalesce and life could emerge, and after billions of years of evolution, nervous systems could develop that are capable of registering quantum facts and thereby constituting physical reality. The universe, if this picture is right, made you so that through you it could become real. This is a sentence that would have been dismissed as mysticism a century ago. It is still uncomfortable in the corridors of physics departments, but it follows with remarkable directness from the three best verified facts in all of physics. That quantum systems do not have definite properties before measurement, that measurement is constitutive of physical facts, and that the universe is fine-tuned in ways that permit observers to exist. The universe, it appears, is asking itself a question, and we are the question being asked. Every act of perception and measurement and observation, every moment of experience, is the universe inquiring into its own nature, reaching across the quantum fog of probability and crystallizing one small patch of definiteness out of the vast superposition of everything that could be. Before the final synthesis, honesty requires a pause. Everything we have explored tonight is scientifically serious. The quantum mechanical facts are established. The Bell experiments are reproducible, and their conclusions are not in dispute. The measurement problem is real. The fine-tuning of physical constants is real. Wheeler's delayed choice reasoning follows from accepted quantum principles. Relational quantum mechanics and QBism are legitimate, peer-reviewed frameworks defended by serious physicists. But the conclusions we have been drawing from these facts are interpretations, not established results. The participatory universe is Wheeler's interpretation of what the facts mean. QBism is an interpretation. The possibility that consciousness is physically relevant to wave function collapse is a hypothesis, not a proven fact. The strong anthropic principle is a philosophical position, not a scientific theorem. We do not know whether observation requires consciousness or whether any physical interaction counts. We do not know whether the fine-tuning of physical constants is explained by a multiverse, by necessity, by design, or by something we haven't thought of yet. We do not know whether the block universe is the correct description of space-time or whether time has a more fundamental structure. We do not know how or whether quantum mechanics and general relativity will be unified, and that unification may change the picture significantly. What we do know is that the simple, comfortable, common-sense picture of a mind-independent reality with definite properties, sitting there waiting to be discovered by passive observers, is not supported by the best physics we have. The world is stranger than that picture. The role of observation is more fundamental than that picture allows. The relationship between the observer and the observed is more intimate and more constitutive than classical physics imagined. The honest position is to sit with that strangeness, not to resolve it prematurely into a comforting narrative, whether that narrative is materialist, where consciousness is irrelevant and the universe grinds on without caring about observers, or idealist, where consciousness creates everything and the material world is secondary. Both of those resolutions close the question before it has been fully heard. The question deserves to remain open. It deserves the discomfort of not being answered. And the discomfort is appropriate, because what is being asked is not a small question. It is the question of what reality is, what you are, and what the relationship between you and the universe ultimately comes down to. There's a moment, if you sit with this material long enough, when the vertigo settles into something else. Not into comfort, exactly, and not into resolution, but into a particular quality of attention, a way of noticing what it is like to be here, perceiving, experiencing, existing a universe that may require precisely this in order to be the kind of universe it is. Look at your hands. Those hands are made of atoms forged in the cores of stars that died billions of years before the Earth existed. Those atoms have been cycling through the universe since the first minutes after the Big Bang. They are entangled through the long chain of their interactions with the rest of the physical universe in ways that have no clean boundary. They are, in the quantum mechanical sense, not entirely separate from the rest of what is. And right now, they are part of a system, part of you, that is conscious, that is experiencing, that is, if the physics is right, constituting a small local region of definite physical reality through the act of perceiving and engaging with the world. You are not a stranger in a pre-existing universe. You're a process the universe is running on itself. You are the universe at a place where it has become locally aware, locally self-observing, locally capable of registering definite facts out of the quantum superposition of possibilities. You're the universe's way of knowing that it exists. This is not a metaphor, or rather, it is a metaphor that has a literal physical core. At the level of quantum mechanics, observation constitutes physical facts. At the level of cosmology, observers appear to be built into the structure of a universe as a condition of its own definiteness. At the level of biology, you are the product of 4 billion years of evolutionary processes that refine the capacity to perceive and model and respond to the physical world with increasing sophistication. At the level of experience, you are the place where all of this arrives at something it is like to be here. The universe is approximately 13.8 billion years old. For most of that time, it existed as a quantum superposition of possibilities, gradually decohering into the classical structures we inhabit, stars and galaxies and planets, and eventually life. Life is the universe's first serious attempt at local self-observation. And you, with your particular nervous system and your particular capacity for conscious experience and abstract thought, represent one of the most sophisticated instruments the universe has so far produced for registering and reflecting on its own existence. Every time you look at the sky and wonder about it, the universe is wondering about itself through you. Every time you ask a question about what is real, the universe is asking about its own reality through you. Every time you experience anything at all, the universe is experiencing itself from your particular vantage point in the four-dimensional block of space-time, from your particular node in the web of entangled relations that constitutes physical reality. This does not make you the center of the universe in the old, discredited, geocentric sense. You're not cosmologically privileged. Your particular perspective is one among a vast and perhaps infinite number of perspectives that the universe generates on itself. The cosmos does not revolve around you, but it does in the precise sense that quantum mechanics suggests require you. Or more carefully, it requires entities like you. It requires observers. It requires observers. It requires systems that interact with quantum states and register definite information, thereby constituting the definiteness that physics describes as the actual properties of the world. Without observers, the universe has no definite properties. Without definite properties, the universe is not, in any meaningful sense, a universe. It is a superposition of all possible universes, none of them actual. The universe became actual, became the specific, definite historical cosmos we inhabit, through the accumulation of observations made by every observer that has ever existed, from the first light that interacted with the first matter to the consciousness reading these words right now. The universe's history is the history of its self-observation, and you are part of that history, not a spectator, a participant, one of the observers through which the universe has crystallized its own reality out of the vast sea of quantum possibility. What does this mean for how you should live? Physics cannot tell you that. What does it mean for the prospect of death, for the question of what persists and what is not? Physics cannot fully tell you that either. What does it mean for the relationship between self and world, between inner experience and outer fact? These are questions that sit at the boundary between physics and philosophy and lived experience, and no single discipline owns the answer. What physics can tell you is this: the common sense picture of a pre-existing, mind-independent universe, chugging along in its definite mechanical way before you arrived and after you leave, is not supported by the best science we have. Something more interesting and more strange appears to be the case. The relationship between the observer and the observed is more intimate, more constitutive, more mutual than the classical picture allowed. You're not looking at the universe through a window. You are woven into it. You are one of the places where it becomes real. And the universe, if it were capable of gratitude, might be grateful for that. Music, slow fade, quiet, something that neither resolves nor ends cleanly. The question the title posed was not rhetorical. The universe doesn't exist without you. Not because you are special in any conventional sense, but because you are real. You are physical. You are the kind of system that constitutes local patches of definite quantum fact through the act of existing and perceiving. And in a universe where that is how reality works, your existence is not incidental. It is structural. The question now is not whether this is true. The question is what you do with it. What it is like to walk through a universe that requires you, not you specifically, but the kind of thing you are, the experiencing, observing, information registering process that produces a perspective to be the kind of universe it is. That question has no answer that science can provide, but it may be the most important question you carry with you when you walk back out into the world. Back into the universe that, in some physically defensible and deeply strange sense, is real because you are there to find it so.